The critical angle no longer exists, and more light is lost. To prevent light losses such as these, optical fibre is manufactured with a second layer of glass of a type that is less dense than the central core. Because the refractive index of the outer glass is lower, the light is always reflected internally. Finally, to protect the glass, it's coated by a layer of soft plastic and an outer shell of tougher plastic. The individual fibres are then stranded together to form a multi-core cable. Even using all these modern manufacturing techniques, some of the light is still lost from the fibre. One reason is that light inside the glass scatters. The rays change paths, hitting the glass surface at angles lower than the critical angle. They pass straight through. This effect is called Rayleigh scatter. We can demonstrate this effect with white light. This drum contains a kilometre of optical fibre. Switch on the transmitter light, and the coil glows blue from the scatter light. It's the same effect that makes the sky blue. The light that travels all the way through the glass and appears at the other end is red. Red light has a longer wavelength than the blue, so the longer the wavelength, the lower the light loss. This is why the lasers chosen for optical communication give out infrared light, totally invisible to human eyes. We can only see it by using special film. This laser light is coming from the edge of a miniature semiconductor chip. As optical fibres are so thin, the light source has to be tiny too. Laser chips are easy to control, ideal for high-speed digital communications. Electric light gives off a broad spectrum of colours, creating the impression of white light. But lasers only produce light of a single colour or wavelength. Because the light is a single wavelength, we call laser light coherent. Light can travel along a fibre in a continuous beam or as digital on-off pulses. Digital signals are made by measuring the analog signal thousands of times a second and producing a series of numbers, each of which is sent down the cable as a binary signal made from on and off pulses of light. No matter how many times the signal is amplified, the same pattern of pulses remain intact. At the distant end, the numbers are transferred back into a faithful copy of the original sound wave. Optical cable carries not only digital voice conversations, but text, data, diagrams, teletext, and television signals. And because they are all digital signals, they can be compressed into minute time segments, allowing many other digital signals to be squeezed into spare time slots. Thousands of telephone conversations or other data travel on the same optical fibre. The amount of information that can be sent along one optical fibre depends on how quickly the laser can switch on and off. Faster flashes means more information. These days, the standard rate is 140 million flashes a second, or 140 megabits. This amount of information will allow almost 2,000 telephone conversations on a single optical fibre. But experimental systems can make this rate 10 times faster and cram 20,000 conversations onto each fibre. A cable the size of a pencil can bring hundreds of television channels into your home. You would need this thick metal cable with all these cores to transmit the same amount of information that can be sent down this one fibre optic cable. Optical fibre is much cheaper than copper. It's made of silica, which is pure sand. Year by year, the price of copper and iron increases, while optical cable is getting cheaper. And there are many other advantages. We can send laser light pulses down a glass thread for about 30 kilometers before the signal is weakened or attenuated and needs to be amplified through a repeater station. Scientists have experimented in sending light signals as far as 100 kilometers without additional amplification. This distance is about 50 times longer than electrical signals sent over conventional metal wire. Optical fiber is easier to install. All this old-fashioned coaxial cable is needed to do the same job as this fiber optic cable. Fibers are immune to interference and crosstalk, and optical fiber is almost impossible to tap. By the end of the century, Britain, the rest of Europe and America will have digital telephone systems, digital data links between intelligent computers, and high-definition satellite and cable television. Glass and light make an unbeatable combination. Essential tools for the digital communications of tomorrow, all made possible by the practical application of the simple physics of light reflection and light refraction.